Hi, welcome to the full version of the talk, Parallel Lotteries, Insights from Alaskan Hunting Permit Allocation. This is joint work with Nick Arnosti, currently of Columbia Business School, soon to be of the University of Minnesota. So let's get started. Quick roadmap for the talk. So I'm going to first introduce the setting. We're dealing with an allocation problem. We'd like to give out goods in the setting one-sided allocation without payments, and we're going to study a mechanism for doing that. Then I'm going to explain the mechanism. I'm going to ask this question, should we ever tolerate wasted items? These are items that we could give away that could be matched to an agent who doesn't otherwise get matched by a certain mechanism. Seems like intuitively the answer should be no, but we'll define that more clearly and talk more about that in the third part of the talk. I'll quickly review some theoretical results that are in our paper in case you'd like to go back in more detail. And then finally, I'll talk about some other applications for this particular allocation mechanism. So our setting is one-sided allocation with no payments, otherwise known as giving things away. In this setting, we have heterogeneous items, so different types of items, different quantities of different types of items, and we're trying to give these items out to unit demand agents, that is, agents who only want one item, who have heterogeneous values. So different agents may have different values for different goods. We'd like to match them up well. Examples of this setting are public schools, so seats at public schools, affordable housing, organs that could be donated, permits for hiking, hunting, fishing, and camping. And what unifies all of these settings is that it may not be appropriate to solve this problem in the classic way of an auction. We don't necessarily want to give these goods away to the highest bidder because we're not necessarily measuring the quality of our allocation as the one that makes the most money or the one that makes the most financial sense to the people participating in it. So with seats at public schools or permits for hiking, hunting, fishing, and camping, you might see why we want to give things away based on need, but not necessarily based on ability to pay. So we can't use that metric. Now, up to a couple of nice conditions, this setting actually has a solution called competitive equilibrium from equal incomes. And this is effectively a virtual currency solution. Agents are given a budget, and then the mechanism computes an equilibrium where all of these agents buy probability shares in the items they want. The prices in probability versus this virtual budget stabilize. And this mechanism has the property that agents' probabilistic allocations are fair. That is, beforehand, every agent prefers their own allocation to anyone else's, otherwise known as ex-ante envy freeness. And they're also efficient, meaning ex-ante Pareto efficient. Before the mechanism goes, there's no way to swap probability shares around between agents to give every agent a weekly better chance of getting something they like. However, there are a couple of problems even with this great mechanism that in some ways solves the system. One major problem is that the competitive equilibrium from equal incomes is too complicated to be used in practice. It's virtually never been used. So we'd like something where the information we have to communicate to and get from agents is within practical parameters. And we also want to explore some questions of sorting. So thinking about what certain preference profiles might mean about agents in the real world, and thinking about certain scenarios in which we want those agents to have advantages or maybe be disadvantaged relative to the population. So we'll introduce that question formally and think about it more later on. Our study is motivated by a particular application of the mechanism we're going to talk about. That is the allocation of hunting permits in Alaska, which is exactly our one-sided setting. So the state has to decide how to allocate hunting permits to hunters every year. And each hunt or each type of good specifies a species that you can hunt, sometimes a subcategory of that species like a mature animal, a location. The state is divided up into game regions and a time window during which you can hunt. And the constraints on this lottery are the quantities of each hunt determined by ecologists, and at most one hunt per hunter. That's our unit demand constraint. How the state has chosen to solve this is by using a mechanism called the 6-ticket parallel lottery. Roughly speaking, they're going to give each hunter 6 tickets and let those hunters allocate as they choose their tickets between these lotteries for different hunts. Let's go into a little bit more detail. We've got, in the parallel lottery mechanism, a separate lottery or bucket for each item. In the picture above, we have item A, item B, item C, and item D. Agents can apply multiple times, that is, put multiple tickets in the buckets, for each item up to a global limit K. So in this case, I've set K equals 3. We have a red agent, a green agent, and a blue agent, and they've all chosen, this is an equilibrium result, to place their tickets in buckets as shown above. So some in A, some in B, some in C, none in D. And then how the mechanism works is that permit winners are drawn until items are exhausted. So we might start with bucket A, draw a winner. Maybe it's the blue agent. So we give one copy of item A to the blue agent. There's another copy of item A left over, so we draw on it again. Maybe it's the red agent this time. The red agent gets the second copy of item A. We then move on to item B. It doesn't matter in which order we resolve the lotteries because of a couple of rules. The first rule, the unit demand constraint, states that every agent can win up to 1 good, which means if you've won 1 good already and you win a second one, you have to choose which one you want and return the one you don't want. And we keep drawing from that bucket until a new winner is determined. So this results in a certain fixed probability of each agent winning each item based on their strategies, independent of the resolution order. This can also be done without real-time input from agents by just soliciting a priority order over items from each agent ahead of time. Formally, we can write the individual decision problem in this case as follows. So remember, you are an agent, you have a certain number K of tickets, and based on some strategies adopted by other agents, you're trying to decide what's your best strategy. Given your values over items, you want to put your tickets in buckets in a way that maximizes your expected outcome. So what you're going to choose, in particular, a number of tickets TI in each lottery, at most K in total. So that's your up to 3 tickets. And you're also going to submit a ranking over all items. And given a certain strategy, you can compute the probability that you win each item based on your strategy. So this formula requires plugging in the TIs and also based on the win probability PI, which is derived from all of the other agent strategies. Win probability PI is the probability that one ticket placed into that lottery wins. So whereas this is interdependent, this is a dynamic system. In a large market limit, you can treat PI and PJ as fixed. In practice, these are often offered based on approximates of last year's statistics or updated and given to agents in real time when this mechanism is actually used. So agents are then going to choose their strategy to maximize this quantity, which is relatively simple, especially when K is small. So this brings up the question of optimal play. Where should you place your 1 ticket? Where should you place your K tickets? And in the general case, we can prove from another paper on a related topic that a sequentially greedy strategy is optimal. What that means is you look at your first ticket, you decide, given the win probabilities, to place it in the bucket where by itself it does you the most good. Maybe that's in bucket A. Then, conditional on having placed that one, you can place your second ticket. In other words, this is a fairly simple, iterative approach that generates your optimal strategy as an agent. It doesn't require searching an exponentially large space. It just requires doing a finite calculation. So optimal play is, at least technically, not very hard for agents. Equilibrium is defined by these endogenous parameters, these win probabilities of each good when you place 1 ticket in that bucket. And these win probabilities are endogenously determined, and an equilibrium occurs when they clear the market. So we have some natural constraints, like, of course, we can't allocate more goods than we have. And if an item is not fully allocated, that means there's less tickets than there are goods of that type, then your win probability is 1. And we can prove that k-ticket equilibria always exist. And in fact, they're unique in the one-ticket case. This mechanism also has some nice properties in the very high demand setting. And what we've proven is that for every agent type, as supply goes to 0, that is, equivalently, the win probability goes to 0, the utility from the parallel lottery over the utility from CEEI converges to 1. So that is, as it becomes less and less likely that you win any particular lottery, we converge to CEEI, this optimal solution. So this is kind of nice and might tell us that we're on the right track. But of course, what we really care about is what happens when demand is not incredibly high or not incredibly low. Both of those cases are relatively trivial. But when demand is somewhere in the middle, how does the parallel lottery work? How does it compare to this more complicated, but in some ways optimal mechanism? Questions like that. So there are two sources of inefficiency in the k-ticket lottery, or the parallel lottery, relative to CEEI. The first is that your allocation is non-linear in tickets. What that means is you put your first ticket in a bucket, maybe you win with probability 1/3. Then you put your second ticket in the same bucket. Your marginal gain, the increase in the chance that you win that good, is less than 1/3 because you have to discount the probability that you win with your first ticket. And that nonlinearity makes it possible for mutually beneficial trades to exist between agents. In other words, this mechanism is not ex-ante Pareto efficient. The second potential problem is that tickets are indivisible. If I have one ticket, for example, I might be torn whether or not to put it in one bucket where I'm unlikely to win anything, but I really like the good, or a second bucket where I'm guaranteed to win something, but I don't like the good very much. The fact that my ticket is indivisible means that occasionally I'll take the first option, I'll bid on something I really want, I'll win nothing, while something I would have taken, I would have preferred to nothing, goes unallocated. So these are two potentially bad things: beneficial trades, mutually beneficial trades, and wasted items. But we'll see that in fact, they're not always bad things. So here's our formal definition of waste. Waste occurs when there are some items left over and some unmatched agents who have non-zero values, that is, they like those remaining items. Here's a particular example where that might happen. You could have an outcome where red gets good A, blue gets good C, and green gets nothing, even though maybe green would be happy with B or happy with D. It turns out that other mechanisms, such as competitive equilibrium from equal incomes, or even a simple mechanism like a random serial dictatorship, that is, shuffle your agents and let them pick sequentially until all items are gone, they ensure that this never happens. However, there's also a blessing to this approach. There's a silver lining to waste. And to explain a plausible scenario, I want to illustrate a case with two hikers, Alice and Bob, and two campsites. The wonderful campsite that's close to the trail and has all the amenities, that's the triple gold star one, and the rural, remote, okay, but not quite as good campsite. And we'll assume that Alice, who is a very competent hiker, has everything she needs in her pack, can benefit from both campsites. She likes the nice one more, but not that much more. Bob, however, maybe a little bit older, has less time, has less resources, needs the amenities available at the first campsite, benefits greatly from the first campsite, and doesn't benefit at all from the second campsite. Now we can look at this simple example and see what might happen under two mechanisms. Under random serial dictatorship, for example, both of Alice and Bob have a 50-50 chance of winning the nice campsite. The expected utility, although depending on scaling, that could be a relatively meaningless number in this case, is 1.4. Importantly, Alice's expected utility is 0.9 and Bob is 0.5. And we can prove, in fact, that if there are two item types everyone prefers type 1, that is the nice campsite, and the number of items is greater than the number of agents, then any envy-free and non-wasteful mechanism, that includes CEEI, allocates this type 1 good, the nice campsite, uniformly at random. So this is an okay outcome. But we can also use a 2-ticket parallel lottery to allocate these goods, in which case the equilibrium looks like the picture to the left. Alice, who I've now given a blue shirt with a very well-drawn blue rectangle, is going to pick the nice campsite with 1 ticket, but she's going to hedge her bets and put her 2nd ticket in the lottery for the not-so-nice campsite to ensure she gets something. Bob, meanwhile, has nothing to lose, so he places both of his red tickets in the first bucket. And in this case, the expected utility is a little higher. Alice's expected utility is just a tiny bit lower, but Bob's is significantly higher. It goes from 0.5 to 0.67. And if you are someone who wants to give Bob a preference in this situation, you probably would have to have external knowledge about what a person with Bob's preference profile is actually like in the real world. If you wanted to favor Bob, it would be great to have this tool, this particular mechanism in your back pocket to make it happen, to give preference to Bob. So I'm running out of time here, so I'll go quickly through our results. With 2 item types and more items than agents, there's a series of thresholds such that agents with strong preferences, that is, like Bob, prefer smaller k, so always prefer 1 ticket to 2 ticket, 2 ticket to 3 ticket, etc. And agents with weak preferences, that is, Alice, who are relatively indifferent between 2 items, they always prefer a higher number of tickets. The picture on the left shows a trade-off based on strength of preferences at the bottom and how well your expected outcomes are. Those are the purple lines for each ticket number. Now, inefficiency from waste. We measure efficiency not on the number of remaining items, but on the value to agents. So the value that they could have given to agents who are then unallocated. We prove that the k-ticket lottery is 1 over k wasteful. So as k goes to infinity, it's perfectly non-wasteful for, say, k equals 3. In the worst case, some agent might get 3/4 of the best possible outcome they would get from a non-wasteful mechanism. We've also proved relatively tight results on trade efficiency. So we can prove that the k-ticket parallel lottery is 1 over 1 minus 1 minus 1 over k to the k trade efficient. And we have lower bounds as well. So, quick summary. Parallel lotteries have several appealing properties. They approximate CEEI when there is a severe shortage of items. They have modest worst-case inefficiency. Sometimes you can achieve better sorting than CEEI, depending on what you think about Bob and what you know about Bob. And in fact, they can be used in other settings. They're used to allocate public housing in Singapore. So thank you very much for listening. Thanks for coming. Have a great rest of the day.